to this computer. Okay, we have a fault here. Yeah.
Yeah.
We have a current flow. Fault current flow. Do we have a current flow here? The answer is no. If we don't have a current flow here, we are not interested of this resistance at all. You see, there is no source, only current flow from a source to the node, yeah? Voltage is zero, you know. Current flows from the higher voltage to the lower voltage, the difference in potential. In the place of a fault, in a node of the fault, the voltage is zero, the lowest possible. It means that all the currents flow to this node. But, how to say, voltage source is only one, it is here. So current flows only from here. From this side, we don't have anything. That's why we could ignore this side. We're not interested. What is the resistance here? Because there is no any impact, because no current flow. That's the reason. No current, no voltage drop, no voltage drop, no impact. This is a serial network, yeah? All the resistors are in serial. That's why. But what have you written here? C7. Okay, this one. Okay, let it be C7, 8, and T6. L8 and T6. No, it's impossible for me to understand the logic. You ignore all this part of
Okay,
resistance.
Professor.
Yeah, I'm just trying to, you ignore all this part, yeah? You have ignored all this. Is ignored. You use this, but there is no source. So, and use this system resistance. Why
Yeah.
have chosen to ignore this part? I don't understand.
I believe that here is the node, so I took the previous element. Is it 7? For example, K13. I took incoming and outgoing current value, everything. But I don't see
Where
it
do you
in
have
C.
the, okay, you have in, okay, do you know the value of ingoing current?
Yeah.
How,
No, but
how
no,
could
no,
you
no.
know? How could you know?
No, no, no. I'm saying incoming values and outgoing. I'm not only the current, because I don't think here is the in the previous drawing. The transformer is connected to the line. So I thought the transformer also providing voltage. That's only I
Okay, so
in the
okay,
first
okay,
page the
okay. If
transformer connected.
yeah, but yeah, I understood. But in a way, if current transformer is providing a current, yes, it is
Mm,
wrong as well. Okay, so you see this transformer, and you have this arrow down. Yeah,
mm,
if you have this arrow down, shows that there is only a load, no any source. But anyway, if you choose that a transformer have how to say is part of the source. Okay, let's go back. Let's go back to this scheme. In this case, we have, because we have three similar transformers, we
yeah.
have current flows that are green. Here we have these current flows, yes. And this is more complicated. This scheme is much more complicated. It's not so easy. Because we need to make the scheme more, how to say, equivalent, and we use this, okay, this flow plus this flow plus this flow plus this flow. So we need to calculate this current. We need to calculate all the current source. How we could do it? No, two ways. If we calculate that this is a parallel branch, this is a parallel branch, this is parallel branch, we calculate the equivalent resistance, yes, and calculate. Or we use, as it is in the first Kirchhoff law, we have, when we have a node, when we have different currents, yes, and we calculate all this, okay. We calculate all this recurrence. Anyway, the calculation is different from this. So, okay, let's come back to the how this should be done. This should be done this way. Right? This way, yes. Because we have only one red current flow and the resistance are in series. So you should add, yeah, only the line resistances. Yeah,
Yes,
or
I
not.
understand.
Okay, but this is not all that I would like to discuss. So you have calculated, yeah?
Yeah,
Node number 9, node number 13, yeah?
13.
And maybe 14 or 11, whatever. So what we do next? We check what is the sensitivity. So
Yeah,
what is the sensitivity for the node 9 and for the node 14, yeah?
yes,
And here you got only one sensitivity, or only for 14, yeah? But
yes.
first of all, you should check the
But
node number
but in
9, because
okay.
this is the main task. And 13 is, how to say, a subtask, yes? So
Mm,
is it good? It is good to be possible to reserve, yes? But the main task is to protect line number 6. So first of all, you should check this one, yeah? Then you should check this one. And
okay,
if
okay.
it is okay for number 9 and not okay for number 13, yes, this protection could be used, but you can write conclusions about, okay, it can't fully protect line number 6 and number 8, yeah, but it is good to know how far could we protect. In case if it is not sensitive for for line 6 or for the node number 9, yes, this protection can't be used, yeah, because it is not sensitive enough. That is the main. Okay, so you should, how to say, finish this task. And okay, so maybe you could put questions, because I would like to go next.
Yeah, and I need to calculate the K13 and calculate the sensitivity for the
You could
lines
go in series. You, for example, could check number 9, number 11, and number
11, 4,
13.
13. Yeah, okay,
And
perfect.
say if number 9 is okay, so yes, this protection is feasible, but question how far this protection could be sensitive, yeah? In case
Mm.
if it is not sensitive for K9, so yeah, the set point is wrong, should choose another one.
What is the range of the good sensitivity point? 1, coefficient is 1.
The good, this is a good, so the main task is to protect its own line, yeah? This is the
Yeah,
main task, yeah? But it could be good if it could protect, yes, all lines in series. So,
okay.
so it is good if it is sensitive for node number 13.
But the coefficient need to be 1, correct?
1.5.
1 to 1.5.
No, 1.5. If it
Okay.
is less one, sorry, I'm wrong. Yes, 1.2. Sorry.
Yeah.
Yeah, the minimum is 1.2. So
Okay.
if it is less 1.2, it is not good.
It is above 1.2 means
Sorry?
it is above 1.2.
Yes. Or equal 1.2. If it is equal, it is okay.
Hmm.
It is minimum okay, but okay.
If it is not equal means what is the solution for the next step?
It could be equal or above. It couldn't be less than 1.2. If it is less
Okay.
1.2, it means that we can't be sure that it will be sensitive.
Hmm.
If it is, we are not sure that the protection is sensitive, so there is possibility that protection will not detect the fault.
Understand, Professor.
So it is impossible to have the situation that we are not sure that the protection could disconnect the fault, because fault is dangerous for the network. Okay, so what I would like to do next for today? I would like to discuss this task. This task
Okay.
is quite easy, but have a little interesting specific moments.
Yeah.
So what we see here. Oh, what we see here. So it is the transformer protection task. So you have a transformer, two winding, not typical, but the easiest one. The easiest one. So there is a power switch, and what we got the information. Okay. Let it be. Okay. I draw more simple because you see the drawing here. Okay, what do we have? What do we know? What we know that the max fault max current is this one. We know that the nominal voltage of this transformer, yes. So here we go 10 kV network, yes. To be true, you know, we have the taps for transformer. Do you know what is a tap of a transformer?
Yes. Tapping.
Yeah, when
Yeah.
it is possible that we during the exploitation, yeah, we could change the tap of the transformer to keep the voltage level, because you understand the could be different loads, yes, different power, and based on this, there is a possible voltage drop. Voltage drop is not possible in the network. That's why we are tapping, yes, transformer winding, yes, to keep the voltage in a possible range. Okay, that's why this is a true transformer voltage 10.5 to 0.4 kVs, yeah. So low voltage is 0.4 kV, yeah.
And high is 10.5.
Yeah. So UK 5.5, this is this special transformer information from manufacturer about the fault voltage in transformer. This is used to calculate the transformer resistance, as you have done in previous task, yeah.
Yeah.
And what we have next is the transformer nominal current in transformer
Nominal current.
Yeah, why we have two values? Because we have a low voltage and the high voltage. Yeah, you know the
Yeah.
transformation. So high voltage it is 55 amps because we have high voltage, and low
Yeah.
voltage value it is 1443 volts or amps. Sorry, amps. So that's why we have two values. Yeah.
The 1443, it is for 0.4 kV.
Yes, it's for no, you know, we have low voltage, we have high current. We
Yeah,
have
yeah, for
high voltage, we have low current.
yeah,
Yeah,
for
because
this
we have the same power.
power, yeah.
That's why we have two different values of current. So the same power is transformed through the transformer, yeah, but different volt amp current values, yeah. And what is important to know why we are calculating this task is transformer tappings. We have two, the step number is 2, and this step is 2.5%. What does it mean? It means that if we have two taps of 2.5, it means it is plus minus 5%. Two taps up, two taps, yeah,
Yeah, for
2.5.
one tapping it is 2.5 percentage.
Yeah,
For two tapping, yeah.
yeah. So we
Understand.
could, yeah, we could increase force. It's 5%. Why this is important? Because in a situation when we are calculating, like it is in previous task, current value, yeah,
Yeah.
we need to know what is the resistance of transformer, yeah,
Yes.
and this transformer is not constant because based on this voltage, yeah, it could be different, yeah. So that's why you should calculate min and max. When we have 10.5 multiple by 1.5, sorry. How to separate the idea that this is voltage. Okay, I'll just this way. Voltage. Voltage, yeah. Or is it clear?
Yes, professor.
Okay, so and what is the idea? When you calculate what is this is very simple task, but very important because here we see the logic, the protection set points. We use maximum current or minimum resistance values. When we check the sensitivity, we always use minimum current or maximum resistance values. That's why when you will calculate. What will be if the fault is after the transformer?
After transformer.
Yeah, so this is the protection. Here it is. The protection is before the transformer. It should
Yes.
protect in case of any fault. Yeah.
Hmm. But about the transformer voltage, the minimum you are multiplied with 1.05. It
Because
is right.
5%.
For the maximum, we are minus 5%.
Volt. So you see, if we have high voltage, we have the low resistance. If we have low voltage, we have the high resistance.
Yeah.
That's why this is a difference.
Okay.
Okay, the transformer nominal power, I forgot, but it is, I think it is clear. Okay, I'm sorry, but I need a 5 minutes break. I assume recording. Okay, so transformer protection. What we need to calculate? Well, of course, the same two types of selective and unselective. E unselective. Let it be 1.2 multiple E K free max and E selective. Okay. A lot of coefficients. Multiple E load. Maximum. So, first of all, what we have the resistance full XC, yep, system plus XT. Yeah.
Yes.
For XC calculation, we use this
Yes.
current value before the bus. So it will be the voltage E.
The voltage will be 10.5 kV, right, sir?
Yep. Maximum. And for transformer, you will have two resistances, yeah? Mean
I need to
and
I
maximum.
need to sum both. I need to sum both. I mean, I need to add both minimum and maximum value, or I can take maximum value.
So every time when you're calculating the fault current value
Mm.
using the Ohm law, you should
Mm.
calculate the resistance and you should choose what transformer resistance you will use, the minimum or the maximum, based on what you are calculating. If you are calculating the minimum fault value or you are calculating the maximum fault value.
Mm.
Is it clear?
Yes, professor. But it depends upon the situation. fault?
Um,
Hello, can you understand?
I'm just, what do you mean the different situation?
If for a transformer resistance, I can add a minimum, right?
Uh,
For Ohm's law, due to
okay.
the Ohm's law.
Of course, you don't know what is the type of transformer for in time of a fault, yes, but when you are calculating the protection, yes, you should, how to say, to check the border, possible border values, border positions. So that's why, for example, if you're calculating unselective protection,
Mm.
you have in formula that you should use maximum
Mm.
current value. Then you should understand, okay, if I want to get the maximum current value, I need to use the minimum transformer resistance value.
Understand.
And in case when you are checking the selectivity in formula, it was written, okay, here, for example, minimum.
Yeah.
So you need to use the minimum fault value. So it's not enough to multiple the free phase current to 0.866 to get it from free phase to two phase fault, but you need to have a minimum current value. So you need to use the maximum transformer resistance when you're calculating this.
Clearly, Professor.
So yes, this is very simple task, but for the main philosophy. What
Mm.
is the maximum? What is the minimum for the protection? What we are
Yeah.
using? That's why I give this simple task. So yes, this is for your homework.
Yes, Professor.
So you should calculate selective and unselective protection and to check the sensitivity.
Okay, Professor.
Yes. Okay. So what I would like to tell you for today more. I would like to tell some words about symmetric component theory or about the sequences. There are a lot of literature, of course, on internet, but I want just to, how to say, make a small review. What is it? First of all, let's discuss the situation. Okay, we have a symmetric three-phase fault. And to be more easier for us for calculation, we use a coefficient like a 0.866 to calculate the two-phase current value, no fault current value. This is possible if we have a series network. But if we have a more complicated network, a loop type of network when we saw previously, yes, when we don't know where is the start or where is the end, we can't so easily calculate two-phase fault current value. And there is a special theory how this could be done. And this theory name is the symmetric component theory. This theory is true for every I forgot, not pair, how it is in English, or it is good for 3, 5, 7, 8, and so on phases system. Yeah, as we use three pair phase system, it is good. We don't. It is quite complicated to calculate when we have unsymmetric system. So what does it mean unsymmetric? We have two fold phases and one not folded phase, yeah? So this situation is unsymmetric. And in this case, how can we use the math to calculate this condition? And to do this, there is a special theorem when we are trying to divide the network into three parts, so-called positive sequence, negative sequence, and zero sequence. So maybe we could use, for example, Google or symmetric sequence. Theory. This is geometric theory. Oh, what is symmetric component? Not source, whatever. So you could see, for example, from Google here, and this is true. So this method is used to simplify fault analysis by converting a three-phase unbalanced system into two sets of balanced phasors and set of single-phase phasor or symmetrical components, yeah? So we trying to represent our network using three parts. Okay, let's talk about how this could be used. For example, still something very simple. For example, source, maybe transformer, line. Let it be transformer, generator, line. So we represent this using three resistance, yeah, and an electromotive force source. It is E, it is how it is represented, yeah. For symmetric fault, it is enough because all three phases are connected together and we got everything the same in each phase. How we could understand what is going on in a case of two-fold? What is going on with faulted phases and what is going on in this third phase? Quite complicated question. And what is the idea of this symmetric component theory? So we use this scheme. Okay. Oops. Let's make a fold here. Okay, two. So we are trying to represent this network with symmetric component. There are two sequences. So positive sequence, negative sequence, and 0 sequence. So 0 sequence if we have a fault to the ground fault.
Neutral.
It appears only. If there is no a ground connection, there is no 0 sequences. Positive sequence if we have a symmetric fault, three-phase fault. If we have unsymmetric fault, not connected to the ground, we have positive and negative sequence. So let's make a table, maybe. We have three-phase fault. It is symmetric. It means that we have only positive sequence. We have two-phase fault, unsymmetric. It means if we have unsymmetric fault, always is a negative sequence. So it means positive plus negative. And if we have one phase fault, it means it is connected to the ground and it is unsymmetric as well because one phase. So that's why it is positive plus negative plus 0. So once more, if we have unsymmetric, it means appears negative sequence. If we have a connection to the ground, appears 0 sequence. Positive sequence, it is always. So it could be positive plus negative, like it is unsymmetric fault not connected to the ground, or we have positive, negative, and 0 when we have unsymmetric fault connected to the ground. How looks positive, negative, and 0 sequences? Okay, this is positive. Typically, it calls, its name is 1. Typically, to be more simple, write plus minus 0 or 1 to 0. It depends on what signs are we using to call these sequences. No, it depends from the past when it was not easier to print, any sign on a paper. That's why there are different different names. So it could be 1 to 0 or plus minus 0. I typically use 1 to 0. So what is the negative sequence? In negative sequence, disappears a source. So positive sequence is a standard representation with elements, our network representation with elements. Negative sequence is the same as positive, but there is no any source. It could be current source, it could be voltage source, no any source. And 0 sequence, let's copy this one. And 0 sequence is here, disappears any source resistance. This is free sequence, how they are. And if we want to calculate, to represent, for example, two-phase fault, we need to use these two schemes. So we need to connect them in one network. If we have two-phase fault, it means that the node of a fault, where is we got a fault, we are connecting and this is their natural wire. This one is a natural wire is connected together and to the ground. This is how two sequences are connected together to one network in case of two-phase fault. So, and you need to calculate current values, for example. This is positive sequence current and negative sequence current, and E is equal E1 plus E2. But we have a three-phase system. And of course, we're interested what is going on in each phase. Yeah. And what we got if we are calculating this current. What phase current do we got? We get in this situation safe phase if we have A, B fault. So here we go with the C phase. Current will be equal E1 plus E2. And if we wish to calculate the A and B, we need to rotate this vector to 120 degrees because we need to multiple E C to this how using this theory, yeah, we could get the value of current for each phase. That's why when we're using this theory, we are always calculating the special phase current value. This is a special phase. And to get another two, we just need to rotate them. This is for a two-phase. In case if we have a ground fault, yeah, it is more complicated and the connection is different. The connection is different. The connection is different. The connection is we are connecting this fault to the ground. This we are connecting to the ground, and this we are connecting here. And this is to the ground. This is if we have a ground fault. We have all three sequences. And in this case, we need to calculate, yes, this network. And to get a fault as a result here, yeah, what phase we get here? Here we go get the fault, the ground fault phase. So in this case, if we have a C phase fault, so we get a C phase current. This is the idea of this symmetric theory. So you see, if we want to get the true current values and to know the values in each phase, yeah, the calculation is more complicated because manually calculate currents for such type of network is quite complicated. That's why for now we are using or math approach, yeah, in matrix form. So there is a voltage potential approach. I think you should hear about this in matrix form, how we could calculate, or a ready-made program when we are drawing a network and the program is calculating the fault values. So there are two ways. Or we use a calculator that could operate with matrix using this, and of course this imaginary values, real and imaginary values, to calculate using this voltage potential approach, all currents and voltage in this network. Or we're using ready-made programs to draw the network, because calculate by hand manually these values is quite complicated. But as I said, this is true, when we have a complicated network, when we have, because here I draw you a very simple, This approach is used for more complicated network, especially for loops. Because if we have a series network, we could use the simplification. As we use, for example, in our task, using only three-phase calculation, only using this positive sequence, only this. Because if you, for example, watch this, this scheme is a positive sequence scheme. Yes, this is this network representation using the positive sequence. And we don't use negative and zero sequences, because network is simple, it is radial, series, and we could just use a coefficient. For example, when we need to use this full approach, for example, when we have generators, if we use a real generator data in our network, we should use, if we want to have very correct values, we should use this scheme. Why? Because what is the difference? Okay, I forgot to tell. Important. This value and this value are not the same. For generator, this negative sequence value is different. And what is else? These values and this are not the same. Here they are the same, but in negative sequence, line resistance is not the same as in a positive sequence. It is about XL0 approximately 3 multiplied by XL1. About 3 times more. But this is, how to say, a very small piece of a big theory. Just for your knowledge that this exists, and where to look it in the internet and what book to read for. Because if we want, how to say, to study this theory, I think we need at least a month. For this calculation. But as I said, for now it's quite easy. There are a lot of ready-made programs when you just need to draw the network to get the fault values. This theory really is needed to know each phase current value. This is the math approach, how we could calculate the current value in each phase. Maybe it will be important in your life, maybe not, who knows, but just I want you to know that this theory exists and how this theory is used.
Yes, sure, sir. It may be useful in future for a PhD. While I'm doing the PhD project, it will may be useful.
I'm not sure because when you are doing something, you're using good programs and
Mm.
all these fault values and currents are calculated in the fault because as I said, this theory was developed hundred years ago. Yeah, it is very
Oh,
old for manual calculation, not using the, how to say, machine. So that's why it is actually it is true because sometimes you need to check the machine and so on. That's why this theory could be used, yes. But as I said, mostly, yes. We just need a tool to calculate current values, and we are using a ready-made tool. We are not, how to say, calculating everything manually. Yeah, it's not needed for now. It is the same way, for example, if we need to calculate the square of the figure, yes, we are not using an integral, yes, we are just using the program. We are calling the function name, and this program using the function name calculate the integral by itself. But it calculates the integral not using the math, but using this geometric approach. When it divides the figure into the small, how to say, trapezia, yes, and calculates the sum of this trapezia to tell you what is a square. So that's why you are not using the integration, you're using a machine, yes, to tell what is a square for now. But as I said, this could be maybe sometimes could be useful. But first of all, I would like you to know that this theory exists and how it works. So if you really want to calculate what is going on in each phase, yeah, you need to draw a scheme first of all to connect all the sequences together based on your fault type, yes, and then calculate all voltages in every node and all currents in every branch. Then you will get the information for the special phase, and this special phase is, how to say, if we have a one phase fault, the special phase is this faulted phase. If we have two phase fault, special phase is the safe one. No, because it's very easy to remember that this scheme can say you the answer only for one phase, for one very special phase. And if we have a three-phase system, with two faults, it is clear that we have the same value for faulted phases and another one for a safe one. And it means that we have the answer for special. Which one is special? The, that is one. Which one? One is safe. And opposite, if we have a grounded fault, one phase fault, one special phase, which one? That is faulted. So it is quite easy to remember. And this one phase information, yeah, it's enough to get the values for two other phases just to rotate using this standard system. If you want to know what is going with other phase, we need to rotate, as I draw it here. This is very short. It's not enough, of course, for understanding, but just for information. Okay, I think it is enough for today.